How does adiabatic quantum computation solve complex problems? Imagine trying to find the lowest point in a vast mountain range filled with peaks and valleys. Now, picture a way to gently guide a ball down to the deepest valley without getting stuck on smaller bumps. That's similar to how adiabatic quantum computation works to solve tough problems. It uses the strange rules of quantum physics to find the best solution among many options. The process starts with a simple quantum system where the lowest energy state, or ground state, is easy to prepare. Think of it like setting a ball at the top of a gentle hill. Then, the system's energy landscape is slowly changed into one that represents the problem you want to solve. This change must happen gradually so the quantum system stays in its lowest energy state the entire time. This is based on a principle called the Adiabatic theorem, which says if you change things slowly enough, the system won't jump to higher energy states. The final shape of the system's energy landscape is designed so that its lowest point, the ground state, corresponds to the best answer to the problem. For example, in an optimization problem, this might be the solution that minimizes costs or maximizes efficiency. As the system evolves, it explores many possible solutions at once thanks to quantum superposition, making it more efficient than traditional methods in some cases. A key part of this process is designing the Hamiltonian, which is a mathematical way to describe the total energy of the system. The initial Hamiltonian is simple, and the final one encodes the problem. The system is prepared in the ground state of the initial Hamiltonian, then slowly transformed into the problem Hamiltonian. The speed of this change depends on the smallest energy gap between the ground state and the next excited state during the process. If this gap is tiny, the evolution must be very slow to keep the system in the ground state. When the process ends, measuring the quantum system reveals the solution encoded in the final ground state. This approach is especially useful for complex optimization problems, like scheduling, logistics, or machine learning tasks. It can also be used in material science to find stable molecular structures by simulating their lowest energy states. Compared to other quantum computing models that use discrete gates, adiabatic quantum computation relies on continuous changes in the system. This can make it more resistant to certain errors and easier to implement in physical systems like superconducting circuits or trapped ions. While there are still challenges in scaling up these systems and maintaining coherence, adiabatic quantum computation remains a promising way to tackle problems that are very difficult for classical computers. It offers a new way to harness quantum mechanics for solving real-world issues, especially in the field of optimization and quantum simulation. Ultimately, it turns a complex problem into a search for the lowest energy state, guiding the system to the best solution through slow, careful evolution.